Hello everyone, welcome to David Griffiths Electrodynamics. Today we're going to be starting our solutions for Chapter 5 on magnetostatics. So today we're going to start with 5.1. And as always, if you're new to my channel, welcome, and returning subscribers, welcome back. If you want to support this channel, you can do so by obviously leaving a like on the video. Subscribing to the channel helps me out a lot, as well as checking out my membership options. I have early access to videos, as well as law tech solutions for some problems. So if that's something you're interested in, go ahead and check those out. But otherwise, we're going to jump into the problem. So problem 5.1 states that we have a particle of charge Q, and it's traveling along here with some velocity V, and then it's going to enter a region that has a uniform magnetic field, B, pointing into the page. The field deflects the particle a distance d above the original line of flight, as shown in the figure. The first question is the charge positive or negative? The second part of the question is, in terms of A, which is the distance, the width of the field region, D, which is the height of deflection, the maximum height of deflection as soon as the charge leaves the field region, and then B and Q, obviously the magnetic field magnitude and the magnitude of the charge. Find the momentum of the particle. So we would need to find the momentum P in terms of A, D, B, and Q. So I kind of just drew this diagram out. So we have the charge Q traveling with some velocity V, and it's obviously just traveling in a constant speed and direction until we get to this region here, which I denoted with these dotted lines, that contains the magnetic field. Obviously, when a moving charge enters a magnetic field, it's going to start to feel a force due to that magnetic field. And the direction of that force obviously is going to be given by V cross B. So obviously, as the charge first enters here, V is going to the right of the page. B is going into the page, so if you use your right hand rule, V cross B is going to be up. So the charge feels a force up, and that's why you start to see this deflection. I kind of drew this bad. This deflection really should be like a circular arc, it kind of looks more like a parabola or something, but it really is like more of a circular arc, because in the example, in a previous example during this chapter, we derive this sort of cyclotron motion that a charge experiences when it moves through a uniform magnetic field like this. So the charge is going to basically, if this whole region was a magnetic field, like everywhere was a uniform magnetic field, the charge would basically move in a circle. But it's only going to move in like a part of an arc of a circle, because once it gets to the end of the magnetic field up here, it's not going to feel a force anymore. So whatever the velocity direction was at the end, it's just going to continue off forever in that direction at that point in time. Now, what is the charge positive and negative? Well, the force is Q V cross B. So V cross B is up. The charge moves up. Therefore, it has to be a positive charge, because if it were a negative charge, then the force direction would be, it's Q V cross B, but if Q has a negative sign, then V cross B being up, but with the negative sign due to a Q, that would make the force point down. Obviously, the force is not pointing down because the charge is moving up. So that means that the charge has to be a positive charge in this case. Now, to figure out the momentum, we know what the motion of this particle is going to look like. It's going to be a cyclotron sort of motion. It's going to move in a circle, but only for the time that it's inside of this region. So I went ahead and redrew this diagram down here. So let's say the charge, is here at the end of its motion. Then this is the distance d that it traveled upwards, right? When it leaves the region denoted by this side and this side, it's gonna, really this should not continue like this, but the motion of it's just gonna be a straight line from here. this distance, this vertical distance is d. That's the height that the particle is deflected. We know, though, that the motion while in this region is basically going to be a circle. So there's some center part, there's some origin of the circle that the motion is circling around, some origin that we're, the center of the circle that we're moving around. So the distance from whatever that point is to our particle Q is r. That's just the radius of this circle that we're traveling along, the charge is traveling along. And if this distance is d, this distance here, then this total distance is r, so this distance here is r minus d. And we can just use Pythagorean's theorem here to say that with this right triangle here, that r squared, the hypotenuse of this triangle, is equal to r minus d squared plus the side of this triangle is a, right? This is a. That's the width of the region. So it's r minus d squared plus a squared. So r squared is equal to r squared minus 2dr plus d squared plus a squared. And we have r squared and we have r squared. So we can subtract that r squared off and get 0 over here. So we have 0 is equal to negative 2dr plus d squared plus a squared. Therefore, we can derive what the radius of the circle is in terms of the width of the magnetic field region and the deflection height. So r is equal to d squared plus a squared over 2d when you just solve for r here. And that's going to become useful because we need the momentum in terms of d and a. And we know the cyclotron formula, the cyclotron formula from, which is equation 5.3, says that the magnetic force, QVB, is equal to mv squared over r, which is the formula for the force of centripetal acceleration. But we can utilize this formula to solve for the momentum because we have both the mass and the velocity in this equation. So if we solve for if we solve for mass times velocity, that will be the momentum of the particle. And r is in this equation, which we solved for. That's the radius of the circular motion, because mv squared over r only applies for uniform circular motion, which the particle is obeying in this case. So solving for m times v here, you can cancel a factor of v. You get qb equals mv over r. Then solving for mv, so we just multiply by r. So the momentum is q times b times r. Then we just plug in our expression for r in terms of d and a. So then the momentum of the particle is q times b times d squared plus a squared all over 2d. And that's pretty much it. It's a pretty short and simple problem. Really just the trick here is knowing that what the particle is going to do. We already solved a situation like this. We know it's going to obey this sort of cyclotron motion. So you have to utilize that fact to sort of solve for this momentum here. So anyways, that's going to cover it for 5.1. So if you guys have any questions, comments, or concerns, feel free to let me know in the comments below. Otherwise, of course, I'll see you guys on the next video.